Okay, are there any questions before we get started? Okay, no questions is very good. So you have a homework to do, and I guess we have learned about diagonal range functions, and we know how they are like now. So you can solve for the diagonal range function in many ways. So one way is to use a Fourier integral, and then you get a Fourier form of this diagonal range function. It might look something like I guess R prime kind of thing. And then what you have then is that you find that when you perform one of this integral, which is what you are asked to do in the homework, this integral is three-dimensional. So if you perform one of the integrals, say you perform one of these integrals first, then you end up with dx dky g tilde kx ky. Maybe kz would be something like evaluated somewhere. Okay, something like this. This would actually be quite a different function. It looks quite different from this one after the quantity deformation. But what you do notice is that there will be some term out here that looks something like this. Maybe a constant here. Okay. What I want you to notice is that this is the PB part. This is the PB part. Because we say that the diagonal range function is always written in terms of a PB G plus something like 1 over K naught squared, or 1 over K naught squared, L times delta R minus R prime. So we say the diagonal range function always looks something like that. And you're asked to show this part. Okay? And this means that if you want to perform the DKZ integration first, it's equivalent to using a disk gearbox. This exclusion volume. Okay? It's equivalent to showing that. It's essentially what I want you to do. And also one of the tricky things is that this part will consist of three terms. You have the M part, and then you have the N part. Maybe with some constant that I'm going to call what it is now. And then the LL part. What you have to show is that there's a pole contribution from here, which I call pole contribution. I will call this a static pole contribution. And then this also has a static pole contribution. And they cancel each other. Okay, these two terms cancel each other. And you have to show that they cancel each other. The reason is because this is an electrodynamic problem. It cannot be a static solution. So if you see a static solution, it has to be cancelled by a static solution from somewhere else. And it turns out that there's a static solution from here that cancels the static solution from here. Okay. In the very beginning, people were always very confused by occurrence of this term. When they solve this problem by Fourier transform, they'll come up with a term that looks something like that, and they do not understand why. And the reason is because you should think of this as a PB term plus a distribution term. Okay, a PB can also be thought of as a distribution. And then in the beginning, people were also quite confused as to why there was a static pole term. If you were to solve the diagonal range function without this term, then the static term would always remain. and they were wondering why. They thought they saw some new physics. It's not true. If you solve it with complete expansion, there will be a curve from here that cancels the curve from there, and then the strange physics disappears. Okay. So I think I need you to show that for the homework. Cancellation of the two terms, and then that you can reduce from this to that a contour deformation. Contour integration technique. Okay. So are there any questions before we move on? If there are no questions, I will conclude what I want to talk about on dialectic Green's function. I'll move on to talk about integral equations. You can read about the other details about dialectic Green's functions, but the other details are kind of involved. So you can read on those topics by your own. I think the essential things about dialectic Green's function you already know. So you don't need to know about the other things in this course, but maybe in the future you need to know them. You'll find that if you solve this problem in different coordinate systems, this term will be different. Okay. So I'd like to move on to talk about integral equation. Which is a very important technique, and we say that when we have a differential equation, we can solve the differential equation directly. For instance, you might have a problem that looks like this. Curl of E of R minus omega squared epsilon of R, E of R. And then you might have a problem with the driving source on the right hand side. This kind of problem has no closed form. And of course, you can solve the differential equation directly. You can put the problem in the box and then make the projection of this problem into a finite dimensional problem and do finite element. The essence of the finite element method is that you find a set of basis functions to expand this set of equations, and then when you do so, you get an equation that looks something like n equals 1 to n, a n. I just plugged it in. This is a finite summation, so there's no problem with changing the differentiation and integration. Okay, and then maybe I can put this even over there. En of r is to the I omega j of r. Okay, and let's assume that we are solving this problem in the box, so that boundary conditions are easily satisfied. We don't have to solve radiation condition, or we don't have to impose the radiation condition. So what do we do? The next step in converting this into a matrix equation. We are halfway there in converting this into a matrix equation. What is the next thing that we should do? We test it. Okay, we test it, and then we should test it with functions that we say is in the dual space of these operations. Okay, and you can identify the dual space quite easily because this part here is magnetic field. Okay, so this part is proportional to H field. Okay, and then the curl of this part, curl of H produces B, I omega B, right? So this part is like a D altogether, electric flux. And this is also electric flux. And we know that electric flux are divergence conforming. This divergence of D has to be giving rise to charges. So if you have a divergence conforming field, you have to test it with what kind of functions? Curve conforming, right? You have to test with curve conforming functions. So you design some testing functions that are curve conforming, that the curve exists, and then try to test this equation that way. Okay, Wn has to be curve conforming. So this agrees with the fact that we often see inner product like this in electromagnetics. This has something to do with stored energy kind of thing. Okay, so we see inner products like this, which means that if this is divergence conforming, this has to be curl conforming. So we take this, and a good curl conforming basis functions are the H elements. Okay, the H elements, you can read up about them from Professor Jin's book, and you just pick these functions to test, and then you can do integration by parts, and finally convert this into something that looks like this. So Wn mu inverse so of En. And then the second term is just, there should be a minus sign here when you do integration by part. And then the second term is just omega squared Wn epsilon En. And then on the right hand side is just I omega Wn R. N is equal to 1 to factor n. Okay? And you have a matrix equation from which you can solve this problem. And we more or less talk about this in chapter 5. What all this means. These are all subspace projection methods. So this is essentially an equation that looks like an bmn n is equal to 1 to capital N equal to, you can call it right hand side bm and the equation. And then you solve these problems. And you can solve this, you can test this with a cavity problem. You can choose the thing to be satisfying the boundary condition. Otherwise, you can put a atomic boundary condition to mimic radiation condition. Those are more difficult issues. I will not talk about those things here. But this is the essence of finite element. But the problem with finite element is that it's very good within homogeneity, but you need to match up the problem everywhere. And then if you want radiation condition, you have to put in absorbing boundary condition. Okay, so those are the two problems that you have to deal with in using finite element method. The fact that you have to match the geometry everywhere. Whenever you have a non-zero E field, you have to match the geometry. And if you want to have radiation conditions satisfied, you have to put in absorbing boundary conditions at PML on the boundary. So a way of avoiding having to mesh everywhere is to use integral equations. A way to satisfy the radiation condition instead of using absorbing boundary condition is to use the Green's function technique. So we learn how to convert this equation into an integral equation and see how we shall do that. Are there any questions so far? Okay, so let's do some scalar wave case first. Okay, there are actually a few kinds of integral equation. One is a surface integral equation. Sometimes it's called SIE. Another one is called volume integral equation. Sometimes it's called EIE. And sometimes this is also called boundary integral equation. Okay, instead of surface integral equation. So you see that in the literature as well. And we use Green's function technique to solve this problem. Okay, Green's function was invented by George Green. And George Green lives from 1793 to 1941. And you see that he didn't live very long. What? What? Okay, 1841. He lives too long. So he lives about under 50 years old. Okay? And he's a miller's son of a miller. self-educated. And he taught himself mathematics and physics. Okay, and he made this contribution when he was alive. So he also know how to make bread very well because he was a miller's son. Okay, but he couldn't write very well. There was an article in Physics Today about his life history. They show some of his letters that he wrote. He always had spelling errors when he wrote. Okay, but he's a self-taught genius. But surprisingly, there are also other geniuses who lived during the period and they don't live very long. Henry Hertz is from 1857 to 1894. Okay, then of course James Clerk Maxwell lived from 1831 to 1879. You see, they all overlap with each other, except for this one. He does not overlap with them. But they all don't live very long, so we should be happy that we live in a modern world, that we have good medical care, and we can live a much longer life than those people. Okay. So, just a sidetrack. I was going to start with scalar wave equation first. Okay, and let's talk about a very simple case of a differential equation like the Helmholtz wave equation that we like to convert into a surface integral equation. And we assume that this corresponds to a two-region problem, that I have K1 in one region and K2 wave number in the second region that have a source QR in region 1. And I can write down the wave equation for region 1, and it will look something like this. And if I write down the wave equation for region 2, it will look something like this, since there's no source for region 2. These are all Helmholtz wave equations. And K1 and K2 are constants. Okay, they're all constants. So this equation has a closed form in a sense, because when this is a constant, there are solutions that you can find for this equation. So we can make use of the Green's function technique in order to solve this problem. So we look for the Green's function in each region. So in region 1, we assume that the Green's function satisfies this equation. Okay, if you put a point source in region 1, then it's like the point source response. And then if you have a point source in region 2, it produces a point source response in region 2. We call that the Green's function of region 2. Okay, G2. Then it's quite straightforward to derive the integral equation from this differential equation by a set of mathematical manipulations and the use of Green's theorem. So the first thing we do is to multiply this equation by G1 R prime. Okay, what is the next thing that we should do? Does anybody know? Yes, Ken, you know?
Integrate it.
Integrate it? That wouldn't produce an integral equation yet.
And dot the other equation with G1.
Which one?
The delta function equation.
Yeah, this equation, you take this equation and then multiply by, very good, okay, multiply by phi1 r. Okay, take that equation and multiply. Now you subtract the two equations. You subtract the two equations, you see that the middle term cancels each other. There's a G1, K1, phi1, there's phi1, K1, G1. K1 is a constant. So when you subtract these two equations, that term will disappear. So you subtract, say, 1 and 2. 1 minus 2 gives you G1 R prime Laplacian of phi1 R prime minus phi1 R Laplacian of G1 R prime. Okay? And then on the right hand side, when you subtract, this right hand side gives you G1 R prime Q R. Okay? And then the other one just gives you minus, when you subtract it becomes plus phi1 R delta R minus R prime. Okay? So when you subtract the two equations, we get that. And the next thing is what? What should we do next? I think many of you are familiar with this because you're in my research group, so you have read this up on your own. And this is kind of revision for you, right? Or for some of the students in my research group, so you know. So what is the next thing that you should do? Yes? Right, before we apply Green's theorem, we have to do something else. We integrate. Okay, we integrate, very good. We integrate over, first over V1. Let's call the outside volume V1, the inside volume V2. So if we integrate over V1, okay, we integrate over V1, then what we get is that the R, G1 R prime, Laplacian phi1 minus phi1 R Laplacian G1 R prime. So you integrate over V1 on the left hand side, you get that. And then on the right hand side, you get G1 R prime Q of R V1. Okay? And then you get the last term. The last term is equal to, depending on where your R prime is. If your R prime is inside V1, okay, the last term will produce phi1 R prime if R prime belongs to V1. Okay? It produces, if R prime is not equal to V1, what does it produce? The last term, if R prime is the observation point of the Green's function, it's the source point and the observation point, you can treat that R prime as the observation point. If R prime is not in V1, what would you get? Zero. Okay, so this is a very interesting thing. You get 0 there. So it jumps from V1 to 0, depending on whether you are in V1. If in V2, you see 0 for the last term. If you're over here, you see V1. Okay? And then we have to apply Green's theorem to this. Yes, can I have a question? No. Okay, no question. So we have to apply Green's theorem to this. So we write G1 Laplacian phi1 minus phi1 Laplacian G1 as the divergence of G1 gradient phi1 minus phi1 gradient G1. Okay? You use a chain rule for divergence. Chain rule for divergence is the divergence of a scalar times a vector is equal to gradient of the scalar dot with the vector plus scalar divergence of the vector. That's the chain rule for divergence. Okay, we take the chain rule for divergence. And if you apply this chain rule, this produces two terms. One of the terms is this. The other term exactly cancels the term that comes from here. This also has two terms. Okay? There will be one that looks exactly like this, and then there will be one that looks like this. Okay, using this chain rule. Okay, you apply this. And then over here, you also produce one that looks exactly like that, and then you also produce one that is gradient of C1 dot gradient of G1. Okay, these two terms exactly cancel each other. Okay, this is the Green's theorem, the cleverness of Green's theorem. So when you integrate this over a volume V1, when you integrate this identity over a volume V1, it can be converted into a surface integral. It becomes a surface integral, ds n dot G1 gradient V1 minus V1 gradient G1. Okay, and that surface is the surface S plus the other bounding surface at infinity. Okay, S infinity. So the surface should be the surface S plus S infinity. Okay, that should be the two surfaces. And we have to argue that the integration over S infinity is 0. Okay, what is the reason that we can argue that the integration over S infinity will make S infinity very, very large? The integration turns out to be 0. What is the argument that we should use?
Sum of the radiation condition.
Summerfield radiation condition, right? What about Mike? What do you think?
Oh, it's because the area of the sphere grows faster. I mean, grows faster than the Green's function, or no, Green's function decays faster than the area. I don't know what I'm talking about. Never mind.
Okay, yeah, it turns out that you have to use some kind of a plane wave approximation. Okay, if you're dealing with static theory, then it's a different thing. But if you're dealing with wave theory, if you deal with static theory, then you can argue that this thing will drop off faster than the area grows. But if you deal with wave theory, what you have is that if you have a source, this source produces phi1 in region 1. Phi1 consists of two terms: a direct contribution from the source here plus a scattered wave contribution from the scatter one. Okay? And if you're sufficiently far away, all those waves become spherical waves. The first thing that you can argue is that all of them would become spherical waves because they're coming from finite sources in the finite region. They become spherical waves. And spherical wave, if you're far enough, looks like plane waves. Everybody agrees? So if you're sufficiently far enough, looks like plane wave. So phi1 will look like plane wave. So you will have IK phi1. Okay? IK phi1, where K is the direction of the plane wave when you're very, very far away. And it tends to align with the direction of the radius. Okay? The Green's function also starts to look like a plane wave. So this also becomes IK G1. Okay, IK G1. Because if you're sufficiently far away, your sources are coming from, where are they coming from? We have to be very careful because we are going to have R and R prime in this Green's function. We're also going to have R and R prime in this Green's function. Our R prime is going to be someplace in the finite region over here when we try to solve the problem. Okay. Our R is going to infinity as this S is going to infinity. So the Green's function eventually will have R and R prime going to infinity. Okay, we have this going to infinity. So any sources that we have in a finite domain will start to look like spherical when we're sufficiently far away. So this term also becomes like a plane wave, and these two k vectors are essentially pointing in the same direction. They might be not pointing in the same direction if you're close to the sources, but you can move the surface further and further away, and the k vectors will point in the same direction. So you see that these two cancel each other. Okay, these two cancel each other. So the fact that everything looks like a spherical wave. A spherical wave eventually looks like a plane wave. Is also the same as a Sommerfeld radiation condition. So because of that, two things, these two terms cancel each other. Okay? Not because, as many students tend to have a mistake of saying that this drops off as 1 over r, this drops off as 1 over r, and this thing drops off as 1 over r squared, and then this integral disappears. But then this surface at infinity also grows as r squared. So there's a wrong argument to say that this drops off as 1 over r squared, and hence it disappears. There's a wrong reason. The wrong reason is that they two cancel each other. Okay, that's very, very important. What happens if you're solving a static problem? The field drops off at 1 over r squared. Why do you think that it drops off at 1 over r squared? What? The potential will drop off as 1 over r if you are monopole source. Okay. The potential will drop off as 1 over r. So the gradient of a potential will drop off as 1 over r squared. The Green function will drop off as 1 over r. The Green function, if I recall, it will remind you, the Green function in region 1 is this one. So if the frequency is 0 for static case, the Green function drop off as 1 over r. This one will drop off as 1 over r squared. The whole thing drop off as 1 over r cubed. The same argument goes here too. This one will drop off as 1 over r squared. This one will drop off as 1 over r if it's a monopole. If it's a dipole, it drops off as 1 over r squared. So for static theory, this term also goes to 0 at infinity. Okay? So we need only to keep this term final. We only need to keep that. And so, what is the meaning of this term? The meaning of this term is the field generated by the source in the absence of the scatterer. In the absence of the scatterer. This term can be converted into a surface integral. So finally, we have a way of writing the solution in the way that I have written in my textbook. Okay. Let me see. I use the same notation. So this is actually minus the incident field because of this minus sign over here. Okay. If this is the source, then this actually produces the minus the incident field r prime at the observation point r prime. Okay. So finally, what we would have is that I will have this equation in my textbook, which I can write it down over here. Which is that if your observation point is equal to V1, I'm going to swap R and R prime. R and R prime are swapped in this equation compared to those equations. There I use R prime for observation point, R for the source point. I'm going to swap them over here as a finite equation. Okay, that you observe the field R, V1R, if you're in region 1, which is this term over here, okay, and then it's going to be equal to incident field. I take this term to the left, the other side of the equation, I get that equation, and then I write down the surface integral term. The surface integral term needs only be integrated over one surface. Remember, I swap R and R prime, so this is the S prime now, N prime now, G1, R prime, gradient of prime, T1, R prime minus T1 R prime gradient prime T1 R prime. Okay, so this is one equation. Okay? Can everybody follow? You get this term from this term over here. I saw R and R prime. You get this thing over here. This is for region 1. Okay, this is region 1. You have this scattering problem. You have region 2, region 1, K2, K1, and V2. Then you have V1. Okay, this is a scattering problem. You can repeat the same exercise. You can repeat the same exercise for region 2 using the region 2 Green's function. There's no source in region 2, remember. If there's no source in region 2, you can repeat the same exercise as in here. No source term, so this term would not be there in region 2. So if you go through the exercise, then you get this equation that for region 2, going through the same exercise, if your R belongs to V2, you get V to R. If R belongs to V1, you get 0. And this term is not there. And because of the way we define the normal now, because if it's region 2, region 1, the normal was defined to be something like this. Yeah, I define the normal to be pointing out of this surface. So if you define the normal to be that way, then in region 2 the normal is opposite to the normal here. So you get a sign difference